typically, MAC addresses are assigned by the IEEE. And when the IEEE assigns MAC addresses, what they do is they make sure that the seventh bit from the left of a MAC address, so if we go in 7 bits here, the bit is going to be a 0. Okay, not the hexadecimal character, but the bit is going to be 0. So we end up in this case with 00 as our MAC address. We come down here, the 7th bit in is 0. Ends up being 0. Well, what they have done is they've decided with the EUI64 format is to flip that bit to a 1. Flip the bit to a 1. So more often than not, you'll always end up flipping that 7th bit from a 0 to a 1. A 0 to a 1. That's what you'll end up doing. Now, if it's a 1 and you flip it, it ends up being a 0. But the odds of ever finding a MAC address deployed to a product that has a 1 there and you flip it to a 0 is almost non-existent. Unless it was a MAC address that was manually defined at some point. But if you go to a Cisco router and you try to change the MAC address on an interface and the 7th bit is a 1 that you put in, it's not going to accept the MAC address. It's going to say it's an invalid MAC address you're trying to put in. And the only reason why is because you didn't put the 7th bit as a 0. So on our Cisco routers, they're expecting the 7th bit to be a 0. All right, but I want you to get comfortable with flipping the bit. So when you practice at any point in time, creating an EUI64 address from the MAC address, always practice flipping that 7th bit. Even if the 7th bit is a 1, flip it to a 0 in those practice environments. That way there, you remember that you're always going to fill the field with fluff every time and flip the 7th bit from the left. More often than not, it's going to be a 0 flip to a 1. But if you're practicing or you're doing an exam or you anything like that, it is on paper, 0 to 1, 1 to 0 doesn't matter. Just keep practicing flipping that bit so you understand how to create EUI64 addresses. So now that the 7th bit is flipped, what do we end up with? We end up with 0, 0, 0, 0, 0, 0, 1, 0. So then when we convert that binary back to hex, we end up with 0, 2. And the reason why is because these first 4 bits here end up being 0, and then these, because this is a 1 now, ends up being 2. Ends up being 2 because that has a decimal value of 2 for that binary bit position. So now if this was a router and it was using link local addressing and EUI64 to come up with that link local address, this would now be the interface ID of that particular IPv6 address. So the network ID would be FE80 and then 00000 until you get to 029027FFFE. So you can always recognize an EUI64 address using FFFE. So if you ever see FFFE, think, ooh, that was assigned by EUI64. Now, this is how we could come up with addresses. So how would this happen here, for example, on a router? Well, we have manual assignment. So essentially, I'm going to the router and I'm saying, your IPv6 address is FF or FE80 :029890, whatever I put in. Or I could say just auto-generate using EUI64. So that's manual methods I could use. However, we also have automatic methods of IPv6 addressing. So one of the new methods we have here that we didn't have with IPv4 is a stateless auto-configuration. It uses the neighbor discovery process. And what's going to happen here is that a router is going to send out a router advertisement that says, hey, I am such and such a router. I happen to be connected to this local area network, and my prefix on my interface is this. My network ID is this, and this is my link local address and whatever else it wants to tell you. Well, based on that information, your device can now use EUI64 and figure out, based on the prefix and the network ID given by the router, what could my address be as part of this local area network? Because you'd want to be on the same local area network as the router. You want to be in the same prefix and the same network. So as a result of that, I could use EUI64 and come up with my complete address, or I could use the random generator and come up with my complete address as well. Did the administrator have to configure anything? No. Any static manipulation of anything? No. So now I know my IPv6 address. I know my prefix, my network part of it. I also know the default gateway because the router says, hey, I am so-and-so FE80 double colon yada, yada, yada. So I'm using its link local address now as my default gateway. Why? Because we're on the same local area network. So stateless auto configuration allows any IPv6 enabled device to dynamically create its IPv6 address without any administrator intervention. But then we still have stateful auto configuration, which uses a DHCP v6 server. So we can set up a DHCP v6 server in our organization and have our IPv6 enabled hosts contact the DHCP v6 server. Now, something you need to understand about stateless auto configuration is that you can only get so much information out of it. For example, I can get my network ID, I can get the prefix of that network, I can figure out who the default gateway is, and now recently, based on newer Cisco iOS operating systems, the router can also tell you who your DNS server is. So I'm not setting up my router as a DHCP server. That's not what I'm doing, folks, with stateless auto configuration. The router just automatically hands out that information using router advertisements, as it's known as. So as a result of that, I don't do anything. I have an IPv6 enabled interface on my router using a /64 prefix, and this happens automatically, stateless auto configuration. But what about other information that's necessary? Right? We're only able to give out that limited information, the prefix, the network ID, the default gateway address, and DNS information nowadays. What about any TFTP information that might be necessary for phones? Or what about any other information that might be required that we typically give out with DHCP? Well, then DHCP v6 is needed for that additional information. So you could either set up a DHCP v6 server to give your clients absolutely everything they need, or you can allow your clients to statelessly auto-configure themselves and then have them just go to the DHCP v6 server for any additional information that they might need. So you can have a combination of the two running together if you really wanted to. But in order to have the combination of the two running together, you have to tell your router, hey, when you send out your router advertisement, tell the client to go find a DHCP v6 server. Go talk to the DHCP v6 server for additional information. Because by default, these clients are set up to use stateless auto configuration. I guarantee you, they are. Any IPv6 enabled interface on a client device is automatically designed to use stateless auto configuration right out of the box. Right out of the box. Now, if there's no router connected to that network that's providing the stateless auto configuration mechanism through router advertisements, then after a moment of waiting, RPC waiting, it eventually says, all right, I'm going to go try and find a DHCP v6 server. So it sends out what is known as a DHCP solicit message to find a DHCP v6 server, which is similar to the DHCP discover message of IPv4, but now it's using multicast instead of broadcasting, and it's called a DHCP solicit message instead. So we will use stateless auto configuration by default in the clients to come up with the IP addressing, but if we don't have those router advertisements arriving, then we'll switch over to use DHCP v6 automatically. There's nothing you have to do about that. It'll happen automatically. So a lot of different addressing options for IPv6. Typically, we are going to statically configure our router interfaces, statically configure them. If we don't want to come up with the interface portion ourselves, we'll use EUI64 for that. But for our clients, combination of stateless auto configuration and probably stateful auto configuration as well.